Hello everybody. Today we talk about prediction. Talking about prediction, we have to talk about what we call the analysis data set. So usually we have a data set like this. Well, maybe not usually, like in the easy case. Yeah, in the easy case, you have a data set like this. This is our cardio data set that we used before. Here we have a list of patients. Each row is a patient. And each row is also what we call a training sample, a training data point. What is done here is that patients have been measured at baseline, and age, sex, smoking status, hypertensive, and so on. And then these patients have been followed up for 10 years in order to identify if they develop chronic heart disease or not. So at baseline, you do not have this information. Yeah, this is what you get from 10-year follow-up. So what you can use this data set for is to build a prediction model where you only have these first variables that you have identified at baseline, which we call our features, in order to predict if a certain patient will develop CHD or not. So this is what we call prediction. It's important that here we have a fixed number of columns, our features. And usually the prediction models need all features to be present, so there shouldn't be any missing values. Most prediction methods are very sensitive in that regard. The target variable, it could either be a categorical variable, in which case we call the problem a classification problem, or it could be a numerical variable, in which case we call it a regression model. Mathematically, we think of this table as a pair of x and y. So these are these pairs of x and y, while x is an n-dimensional vector, so from age to systolic blood pressure, and y is a numerical value. So even though it could also be categorical, then you place -1 and 1. We think about this as these xy pairs, yeah, with a high dimensional feature vector and a one-dimensional target vector. In practice, often you do not have the analysis data set right away. A data set which looks like that, which looks pretty much like one table, and you have a set of features which are all complete and one target variable. So usually you start with some database, and then you have to develop your analysis data set. Yeah, think about the features, think about the target variable, and so on. So based on the analysis data set, what you do is typically a split of the data. So you take one part of the data, for instance, 70% of the data, which is your training data, and the other 30% of the data you keep for testing. The idea is that you try to build a prediction model based only upon the training data. Yeah, the training data is used for training to get a prediction model, which is some kind of function or procedure or algorithm that can be used to compute the target variable based on the input features. So the model is a function that takes this input vector x and computes a prediction, yeah, a value that should be the target. And if you have a good accuracy, then you compute the target correctly. But sometimes you will miss it. And then in the test case, so for the test data, what you do is then you use the prediction model in order to predict all target variables. And this is what we've done here. And then you can compute some kind of a metric. A metric, in this case, the accuracy, which tells you how good your prediction is. So why do we do that? Well, the idea is that you will get a performance estimate here by splitting up the data and training only on the training data and then testing only on the test data. The idea is that the performance you will see here is some kind of a fair evaluation of the performance of the model. So the idea is the performance you will see here is the performance of the model seen on unknown data. So when you use the model in a production environment where you do not have the target variable, you only have the input features, and the model is used to compute some valuable predictions, the idea is that the accuracy the model will have in the application phase will be the same as you've seen here on the test data. But what is machine learning? Well, machine learning refers to a set of methods to solve certain kind of problems in the field of learning from data. So there are these classification methods used for predicting categorical variable. Then we have regression methods used for predicting a numerical variable. And well, then there is a clustering and dimensionality reduction, which we will tackle later in the course. This is the core slide of prediction. So when you have a prediction problem and you want to use prediction, you have to identify 4 core parts of your prediction problem. First of all, you have to specify the data. So what does your data look like? As we talked about before, we need these pairs of x and y, where x is an n-dimensional vector and y is a one-dimensional numerical value. So you need to specify exactly what are your input features and what do you want to predict. Yeah? And then you need these pairs where the feature set x corresponds to your target variable y. Okay, you have to specify the data. Then you need to specify a model, and a model is just another term for a function that has a lot of parameters. A model is a function that takes x as an input and computes y hat, your prediction. And the function could have several forms. Yeah? It could be a very simple linear function, could be a quadratic model, a quadratic function, could be a tree model or a deep learning model. And there are all kinds of models. Yeah? But they're all just parameterized functions with parameters that takes an x, this x here as an input and computes this y as an output. The question is like, what kind of model, what kind of function should you choose? And the idea is that it has to kind of match the data. Yeah, then some models just perform better on certain data sets than other models. And this is what we need to find out when we work on a prediction problem. Then there's the loss or the error model. The error model specifies how good your predictions are. You have your predictions and you can compute your predictions based on your test set. And then you get your y hat. And then you compare the y's to the y hat in order to see how close are these, how good are your predictions. And there are several ways to do that. A typical way for numerical y's would be to compute the mean squared loss, the difference between these two, and then you square it and then you sum up over all your data points. For categorical variables, you could compute the accuracy, for instance, or the cross entropy, which is very similar to the accuracy. It has a few numerical properties. More precisely, it's differentiable, so it can be used to further improve the model performance. That's the loss. Yeah? How good are your predictions? And the fourth part is the optimizer, the so-called fitting, or you may call it the training phase. So in the training phase, you use your training data in order to find a set of parameters better that perform well on the model. Well, what does perform well means? Well, it means that it minimizes the loss over your training data set. Argmin means that you're looking for the better that gives you the lowest value of your loss function, yeah, for all your data points. And it depends on the kind of function, on the model you're choosing, what kind of optimizer you need to choose. The good thing is that in all these machine learning packages, the model and the optimizer is kind of already implemented. So they're easy to use packages, so we do not need to worry that much about it. But in principle, these are the 4 parts you need to take into account and you need to be aware of in order to fully describe prediction algorithm. There are actually hundreds of machine learning models you should know and understand. But put together this list of very fundamental machine learning models or machine learning algorithms. And you should really have an understanding of these basic algorithms. For instance, there's linear regression and logistic regression. These two are the prototype machine learning algorithms for the regression task and for the classification task. Nearest neighbor is a very simple algorithm where you just look on at a data point, what are your closest neighbors in the feature space, what do they say, and then you kind of agree with the majority of them. Then there are these tree models, like simple trees and backed trees, support vector machines, and deep learning models. So each of these machine learning models has certain advantages and disadvantages, and they have all some kind of key ideas that you should at least heard of and be aware of. In this course, I won't be able to talk about all these methods in detail, but I put together a very good list of YouTube explanation videos. So all these videos come from the YouTube channel StatQuest, which is just an awesome resource. I mean, they put together these 15 to 25 minute videos per machine learning models, and they explain it in a very excellent way. So there's no need for me to kind of replicate that. That's a good starting point, to get an overview of the methods, what's out there, what are the key ideas. And then you will find out that there are much more methods, but they're all just a recombination of some basic ideas. So this, even though it's a very short list, it gives you a good overview of the field of machine learning algorithms. So we have all these different machine learning models, but which one should we choose for a certain application? Well, there are certain criteria you need to look at. For instance, the accuracy. Obviously, you need to have a model that is very accurate. A model that gives you 90% accuracy is obviously better suited for your problem than another model that gives you only 85%. But there's more that needs to be considered here. For instance, interpretability is very important, especially in clinical applications. A doctor just needs to know why a patient should take drug X versus drug Y. So interpretability, not only for clinical applications, is a core part of machine learning. You almost always want to understand what are the important features and how they come into play. Simplicity, efficiency, and scalability might also play a key role in your application. Maybe you have a very large data set that you need to scale out over several machines. Maybe you have very limited compute resources where you want to apply your model. And usually simple models are preferred over more complex models. It reduces the amount of headache that you have building and using the model. So there are really a lot of things that need to be considered when you choose your machine learning algorithm. And the accuracy is the thing that we often look at first, but it's not always the most important criteria. There's definitely more to be considered here. Now I would like to talk about the performance evaluation of a classification model, as there is some nuance to that. So we have this application we're going to talk about. There's some car manufacturer that produce motors, and before you put these motors in vehicles, you have to test them in order to verify their functioning. So what they do, they put these on a test bench and then let them run. in order to measure them by acoustic sensors and also by vibration sensors. So you end up with a bunch of sensor data that historically was visually inspected by the mechanics. So, and then you can use this data, so these pairs of the sensor data and your labels produced by humans in order to train a model. Okay. Then, if you have a model, you can use the unlabeled sensor data in order to predict the label, which hopefully is as good as the labels from the human, or even better, maybe. And here we see the performance of one of these models. And we call this the confusion matrix. So we trained the model on a training data set and then evaluate the model on the test set. And here we see the performance of the model on a test set. On this axis, we have the real value. So what the humans have said. And then here on this axis, we have the model predictions. So okay means the motor was good, there was no defect. And then there are some kinds of defects that might have occurred. Yeah, Nockenwellenfehler, Schlepphebelfehler, Zylinderkopffehler. So I'm not a vehicle expert, but these are some kinds of parts of the motor which may have problems. And there's also the case of other failures. So are the model predictions good? What do you think? Well, for instance, let's assume we have a motor that has a Zylinderkopf error. So one of these cases. And there are quite a bunch of these. So maybe I need to point out that these numbers are made up. They're not real numbers, okay? So, but let's assume we have a Zylinderkopf error. Yeah, the real label was Zylinderkopf error. And then the model, in the most cases, actually said it's okay. Okay, so what happens now? What happens? Well, this motor is put into a vehicle and then provided to the customer. The customer drives off with this vehicle. And then maybe after a few kilometers or a few hundred kilometers, the motor got broke. So what happens then? Well, I guess the customer is very pissed and he brings the vehicle back to the dealer, and the dealer has to provide a replacement car. And well, the motor has to be fixed now, which obviously is a bunch of cost associated and also, yeah, a bad customer experience. So this is actually something that is very bad. Yeah, that the model, if the motor is broken, predicts that it's okay. Yeah, that's actually something that you want to avoid. Definitely. So what happens if the model, let's say, predicts it's a Nockenwellenfehler? What happens now? Well, I guess the mechanics will change the Nockenwelle and then retest the motor. And then it depends. Yeah? Maybe then the model will say it's okay, or then maybe it will find that it's a Zylinderkopf error. So in that case, what happened is that there's an unnecessary repair that has been done. Yeah, there's definitely cost associated with that, but it's not as high as the cost associated with assuming the motor is fine and provided to the customer. You see, all of these different cases, they have different costs and different outputs associated with them. So for certain applications, you really need to take into account these different outcomes of several kinds of prediction errors. Well, what happens if the motor is actually okay, but, well, the prediction is a Nockenwellenfehler? Well, then obviously you have another kind of an unnecessary repair. So basically what you want to see is that all numbers are on the diagonal. But you see that's not the case. Yeah. But is the model actually performing good? And the key idea is, in the total sense of accuracy, it seems to perform very well. So you see that almost all motors are okay and also are predicted as okay. So that's 88,000, and all these other numbers are rather small. Maybe they end up to 2,000 or so. So it's like 88,000 out of 90,000, so far more than 88% are predicted correctly. Yeah, that's a very high accuracy. There's almost no error associated. The error rate is really small. But there's these certain types of errors that are associated with a high cost. Therefore, you want to avoid these kinds of errors. So the point I want to make is that the accuracy is not always a good indicator of a model performance, especially if there are unbalanced classes. Okay? If you have one class which is very huge, let's say one class makes up 99% of the cases, and then you have another class which is only 1%, a very rare event. So a model that would predict always class A, the most prevalent class, would get an accuracy of 99%, even though it hasn't learned anything. It just predicts always class A. And therefore, only looking at accuracy often does not tell you the whole story, especially if you have unbalanced classes. And unbalanced classes are quite common. And then there are these different kinds of errors, and they might have different costs associated with them. And in certain applications, you would definitely need to address these costs in order to avoid some kind of errors. And you can try to optimize your model in order to avoid some kind of errors. That's a rather complicated case with so many different outcomes, so different labels. Often we only have two labels. So the two class case is very common. For these two classes, we usually talk about the positive class and the negative class, to make it kind of simple. And what's your positive and what's your negative class is often up for debate. Let's talk about an HIV case. So HIV positive might be the positive class, but it's not really associated with some kind of positive outcome. That's a matter of definition, what your positive class is. So, and we again have a confusion matrix, but it's rather small. We only have two different values, two different real values on this axis and two different predicted values on this axis. And these cases we name true positives. There are positives and they are also predicted as positives. And these are the true negatives. And then we also have the false positive and the false negative. And then there are different rates we talk about. We talk about the true positive rate. That's also called the sensitivity. This is when you think about the corona tests we had some years ago. There was this PCR test which was very sensitive. You could almost always identify any infection, but it would take several days. And there was this oral test or the nose test, which is not as sensitive. There were a lot of cases that were missing. That has a lower sensitivity. That's a proportion of the positives that you have identified correctly. The specificity is like the oral test also often had false positives. It would say you're positive, but actually you only had a flu or something like this. So this had also a low specificity. You couldn't be sure that a positive result would actually be real positive. You would have to retest again. Retest using then a PCR test which had high sensitivity and high specificity, but high cost and long delay times associated. Then you could also turn it around. You could also talk about the false positive rate, which is basically 1 minus the true positive rate. False negative rate is sometimes called the harmful error rate. So there are these very severe errors you would like to avoid. Like in these cases, to have a motor that actually has a failure, but it predicted as okay. So this kind of errors you would like to avoid. Yeah, that's when you talk about a very low false negative rate. The proportion of positives which yield negative test result. So it is actually positive and you would really like to catch it, but you predicted it as a negative, and therefore you missed a positive. And commonly used is also the precision. It's the proportion of true positive predictions among all positive predictions. The proportion of true positive predictions among all positive predictions. So what happened here is that you predicted too many as a positive. You know, there were too many. Some of the positives that you predicted were actually not real positive. There were also some negatives there. That's sometimes these kinds of errors have a high cost and you would like to optimize for that. So all of these rates you can compute using this confusion matrix. And it usually looks like this. Yeah, you say these are the TPs and the TNs, true positives, false negatives, and so on. And then you have some kind of formula that you need to apply. Usually there are software tools and libraries that can compute these numbers for you, or you can compute them by hand. And if you're missing one of these formulas, you can look them up usually on Wikipedia. They have a very good summary there. So commonly, I tend to use sensitivity and specificity, these two. But it's also very common to use the sensitivity and the precision as two metrics for evaluating the performance. In order to optimize a model in terms of sensitivity and specificity, what you have to do is to optimize the cutoff. So what's the cutoff? Well, the prediction models, they usually give you a score. Yeah, they compute from the high dimensional space, they compute some kind of a score. And then we have a cutoff in order to determine which are the positive cases and which are the negative cases. So it might look like this. So we have a score from 5 to 15. Yeah, could be any range of numbers. And a good score would allow you a good separation of your classes. So here we have all the positive classes, and the positive classes, they have a rather low score. And here are the data points of the negative classes, and they have a rather high score. And you see that the score is not bad. Yeah, it allows for quite a good separation of the data points. And then you draw some line, some vertical line. For instance, this red line here, you may draw it at, I don't know, 7.7, something like this. And then you would predict all that are left of the red line as the positive class and all that are right of the red line as the negative class. Yeah? And this would give then rise to this confusion matrix. Yeah? This would give you the actual predictions. So when you look at it, well, from the positive classes, so from all these data points, all these here, these seems to be 7 data points, they are predicted correctly. And these 2, they are predicted incorrectly. So there are actually positive classes, but they're predicted as negatives. On the other hand, we still use cutoff 1 here. We got 1 misclassification. So that data point here is left of the cutoff. So we would predict this as a positive class. And all these data points would be predicted correctly as negative. Yeah, so we got 1 false positive prediction. Yeah, 1 false positive. So this cutoff then would actually be high specificity. Yeah? High specificity means that your model is very specific in terms of if it says it's negative, then it usually is negative. On the other hand, cutoff 2. Cutoff 2 is the blue line here. And what cutoff 2 does, it got rid of all the false negative predictions. So here for cutoff 2, all positive cases are actually predicted as positives. This is a cutoff that gives us high sensitivity. Yeah, we don't miss any of the positive cases, but that comes at a cost. It comes at a cost of much lower specificity. Yeah? We have much more false positive predictions. And well, that's kind of in the core of statistical learning or machine learning, that you tackle problems that are statistical of nature, and therefore you don't have usually a way to find optimal solutions, where you can have 100% accuracy, where you get every data point correct. Because the problems we're trying to solve are inherently of statistical nature, and there's noise and randomness involved, and therefore you never get, or usually almost never get, 100% accuracies. And therefore, you have to make decisions. Yeah? You need to optimize the cutoff in a way that fits your application needs. What do you want to avoid? You want to avoid the false positives, or do you want to avoid the false negatives? So the thing is that in order to optimize for sensitivity and specificity, or even compute the sensitivity and specificity, you need to specify the cutoff first. And the problem is that you do not know the cutoff in the learning phase. The cutoff is something that you also have to learn additionally to learning the score, the separation score itself. And when you evaluate the performance of a model, it's actually kind of cumbersome to always learn the cutoff. And therefore, we have a way of evaluating the performance of a classification model independent of the cutoff. And the way we do that is we just take into account all cutoffs. So we try out every possible cutoff, and each value of a cutoff gives us 1 point on this receiver operator characteristic curve. So one cutoff gives us a sensitivity of maybe, say, 80% and a sensitivity of maybe 30%. Another cutoff gives us this data point. Once we specify the cutoff, we can compute the sensitivity and specificity, and this gives us 1 point on this ROC curve. And the AUC, the area under this ROC curve, is a good evaluation of the performance of a model which is independent of the cutoff. And therefore, you do not have to learn the cutoff when you want to evaluate the model. So a random model would give us this ROC curve here. It's just in the middle of the two, and it gives us an AUC of 0.5. The model A has actually learned something. It's definitely above the random line. And an even better model would be model B. You see, for a given specificity, you get a much higher sensitivity. And therefore, you get a higher area under the curve. And in total, this would be a better model. Perfect model would be shooting up right here. It would give you 100% specificity and 100% sensitivity. Or a very, very excellent model would actually be very close here. Yeah, it would be very, very close and would give you an AUC of close to 1. Next, I want to talk about performance evaluation for regression models. Well, for regression models, the whole story is a little bit simpler. There's not as much nuance as for classification models. So in this case, we have a linear regression. Yeah, we have some x and some y. And for this one-dimensional regression problem, we put a straight line here. And then the error is the deviation of the predicted value. The predicted value is the straight line to the real value. So this difference here is the error we are making. And the performance metric that is usually used is the mean squared error, which means that you sum up all these squared errors and divide by the number of cases, which gives us the mean squared error. And yeah, there might be other ways to evaluate the performance, but this is definitely most common one. And you can use that for any kind of regression model. It's not only applicable for linear models. And with that, I would like to conclude the first lecture on prediction. And the next video, we will talk about cross-validation, which is a key idea in machine learning and prediction models.